And so that's the last time we go over the selectivities. Okay, what was this? So last time we stopped here. This is the alkane, and we go through the halogenation or chlorination in this way, in this example. So chlorination of this reaction, it gives us a series of products. And all these reaction products, it come from the reaction intermediates. And so, for example, this reaction product, it comes from the a carbon free radical with terminal carbon losing the hydrogen from the free radical, because the reaction, the way this reaction mechanism is, this reaction mechanism start from the initiation and propagation. There are many steps after initiation, which we form the chlorine atoms. Those chlorine atoms will react with this carbon-hydrogen bond or this carbon-hydrogen bond. Or there's only two types of carbon-hydrogen bond in this molecule. And so the next step, free radical, you could have this free radical. And also with the terminal carbon lose hydrogen, this radical. So the reaction mixture have 3 free radicals in the system. The chlorine atom and 2 kinds of different carbon free radicals. Realize this carbon free radical is much more stable. The tertiary carbon free radical, just like cations, much more stable than the terminal primary. And so this is more, reaction will be faster because more stable, lower activation energy, and in the end it will give us major products. So this should be the major product. And about this reaction product, the reaction of this kind of product, it should be fairly significant because number of hydrogens available for this reaction, there are 9 of them. There are 9 of such hydrogens, the terminal hydrogens. So just by statistics, the chance of bumping into the chlorine atom and react is just very high. So this would be a secondary minor product. This is the most important. And this will be the secondary. What about the other product? Okay, the other product we have, this product is easy to understand. This product comes from 2 of such free radicals. 2 of such free radicals form bond. So the form bonding of this radical, use arrow pushing, it'll be like this. A single hook arrow, and these 2 will run into each other and form the final alkane. This product, it comes from the this. This is the most abundant product, but once you form the product with the halogenation reaction, it's not easy to control, make it stop, because this being the major product, there are still carbon-hydrogen bond available. So those carbon-hydrogen bond can still react with the chlorine atom and give you radicals and give you, so this is basically chlorine radical react with the product. First, the primary product give you, this is the minor, becomes one of the minor product. So the free radical reactions can be complicated. Well, as a matter of fact, the most organic chemical reactions are complicated. Getting the more than one product is very common among the organic chemical reactions due to the lower reaction rate. Since the reaction lower rate, there are many competing reactions can happen at the same time. So you get more than one product. The bottom line is this will be the major product, and the others all minor. So the halogenation reaction, we use the selectivity, the preference of forming tertiary carbon radicals as the most stable, and then secondary and with primary carbon radical as the least stable, the most highest energy, it can be used for the selective synthesis. And this is example, the draw the structure for with this alkane, which is actually alkene. This alkene reacts with the bromine, and when you see with light reaction, this should give us a free radical reaction, because bromine bond is very high energy and easily can be break by the high energy light, form the bromine atoms, free radical, and the radical will have all the reactions. If you remember in the alkene chapter, and not to confuse you, but now we can see there's some kind of a similarity but difference. Alkene and bromine, there can be the addition reaction, but that reaction is in the solvent. Very common solvent. It is non-protic, a non-polar solvent such as the carbon tetrachloride. When you have the alkene in the bromine in the carbon tetrachloride, that reaction, simple addition reaction, goes through the bromonium cation and give the final, the 2 bromine, 1 on each carbon, give you that product. But for this with light, the reaction will be 3 radical reactions. And 3 radical reaction, the selectivity is based on the structure of the carbon, what kind of bond they break. So anyway, with this and with this reaction condition, the product should be just the halogenation reaction, which is sort of a substitution reaction. Okay, halogenation is almost a substitution reaction. So with this structure, and then we realize how many different kind of, we need to first show where the hydrogens. So there's hydrogen here, and this is hydrogen here. At least there are 3 of them. Okay, there's 3 hydrogen here. And here's hydrogen. Here's hydrogen. So if each hydrogen here given a chance to react, then we would get 1. This is same as the other one. Okay, if only one of the hydrogen will react, how many different kind of product we can get? These 2 hydrogen, because both are methyl group, exactly same. So the unique product, this is the only one, because the reaction, if takes place on this hydrogen, will give me the same product as this hydrogen being substituted. So this one I will not count as a new product if the reaction happens on this hydrogen. And the other one, this is the second one. And this methyl group is different. This methyl group is different from the other methyl. So number 3, number 4, and 5. If the reaction react in the possible as a monobromination reaction, there should be 5 different products, mono substituted. And so if we draw those 5, there's just a lot of lots of drawing, but nothing really, just nothing really. This be the first one. First hydrogen be substituted by the bromine, and so the second one will be this. Okay, will be this carbon. Bromine is here. All right, so this will be the second monobromination product. And we can keep drawing the others, but anyway, all the others are fairly easy to draw. Just replace the hydrogen that I showed here by 1 single bromine. You get all the 5 product. Okay, so the next question, this is getting more interesting, more important. Which product is more important? We rank the product in order from most major to most minor. So basically we need to rank each one product. So this is based on the the stability of the carbon-free radicals. The other factor, it is the if stability is the same, then the more such kind of hydrogen available, then just because statistics, the probability should be higher. And so basically, there are two factors. One is the stability, carbon radical stability. And the other one is the number of hydrogens. If the stability is the same, the number of hydrogen atoms, how many such hydrogen atoms available? Then you have the more it's the same kind of hydrogen available, then you have higher chance to react. And so we have all these four different possibilities. And obviously, this is a tertiary. This will be the most stable. So the product number 2, which is a tertiary carbon radical, should give you the most product because it is more stable. And therefore, because the Hammond postulates, more stability, more stable than the lower activation energy. So the product number 2 is the most, should be the most. Another factor is the bromination reaction is very selective, as you can see the last time, is many times more selective than the chlorine. And so for the bromination reaction, stability of the carbon radical, that's number 1, the most important factor, as you can see from the previous discussion. Okay, so the tertiary carbon radical will give you the most product. What is the number 2? Tertiary carbon radical is most stable. The second most stable is the secondary carbon radical. Among the hydrogen 1, 3, 4, 5, which hydrogen is on a secondary carbon? So the rest are here. Which hydrogen is on a secondary carbon?
Number 4.
Number 4. So number 4 is secondary carbon. If that one lose hydrogen, become radical, is more stable than the others, than the primary. Number 4, it should be the second most stable radical. So to give you the second in the amount of product, it's also with the rank second because more stable radical, lower activation energy is faster, give you more product because it's secondary carbon. Okay, so now we have down to 1, 3, and 1, 3, and 5. 1, 3, and 5. The talking about the number 1. The number 1 is a methyl group, and it has twin. By the way, it has a twin brother. This methyl group is a twin of this. So either one of these, if one hydrogen react, will give a product that is just it is this product. Since the position 1, there are 6 hydrogens can react. Position 3 have only 3 hydrogen, a single methyl group. Position 5 is also the single methyl, the CH3 group. The position 1 have twin. There are 6 hydrogens. So in the position 1 to react, the product number 1, it should be the amount of 3. It should be more, just because there are more such hydrogen available to be extracted to be replaced by the bromine. And so 2, 4, 1, and then we have 2 more. Positions 3 and 5. Positions 3 and 5, these 2 both are a methyl group. I think these 2 reactivity should be similar. It's going to be very difficult to compare between 3 and 5. So 3 and 5, I will just put it in between these 2 kind of both are in the lower bottom, in the rock bottom. So because 3 and 5 is the differences are very small. And they both are primary carbon radical to give a product. So I would rank these 2 as the bottom, the least amount of product I can get. So this is how we use, we predict what will happen with the alkane react with halogenation reaction. We compare the carbon radical stability first, and then we compare the we compare the number of hydrogens available for such a reaction if the carbon radical stability is the same. So the position 1, 3, and 5, they all methyl group lose hydrogen give to replace by the bromine. Then the more of such hydrogens in this position, we have twin. So it's just more chance of getting a substitute by the bromine. So that's the discussion about the ranking the amount of product from the reaction. It is stability is the most important. Yeah. So that's the reaction. The reaction would give you, it's possible to form a chiral center. And that's when the mono halogenation takes place. So those hydrogens, among all the hydrogens in this alkane, only one hydrogen being replaced by the halogen. This monobromination only if when the butane or even more complex. And so for example here, if the reaction happens here, which is the major product, this will be the major product because secondary radical. It could have a chiral center, but because the free radical is the, we treat it as a trigonoplanar structure, even though in reality it's a quick flipping back and forth trigonopyramidal, but because the average by average is a trigonoplanar, and that's why the free radical by average can be just considered as a trigonoplanar. And with the trigonoplanar, the after initiation step, during the propagation, you form the carbocations and then react. The free radical trigonoplanar can attack the other molecules from both sides. So it gives the racemic equal amount of the RS mixture in the reaction. Give it racemic. So in this regard, it's similar to the carbocation reaction mechanism. Okay. The planar is not exact planar. Keep in mind it's by average planar. Yeah, so this shows you the trigonoplanar. This is the either considers perfect trigonoplanar a static trigonoplanar, or the average between the flip-flop. The radical single electron can be on one side of the plane, or can be quickly reversed to the others because the electron quickly moving back and forth at the extremely high speed. So by average, these two, the average will give you essentially the trigonoplanar. And that'll make the reaction can go both ways. So next, a little practice on, okay, draw all the monosaccharides that would form in below, including all stereoisomers. This is a more complex alkane. And we need to know where are the hydrogens. The halogenation reaction, it is essentially can be considered as the hydrogen, one of the hydrogen replaced by a single halogen. And so we need to know where are the hydrogens. So hydrogen here, here, here. So these are all the hydrogens available. If we're talking about mono substitution, this will be a one product, a new product. This is a methyl group, which is same as this methyl group. These two are identical. So again, we get into a twin situation. Since they're dealing with twin, this will give you a monohalogenated alkane, but the halogen on here, it should be same as the halogen on here because of quickly freely rotating structure. So, but let's just count this one as keep in mind these two is almost identical. The only difference, they are the enantiomers between these two, the halogenation taking place, giving a pair of enantiomers. And of course, this hydrogen can be lost. Well, probably the easiest because tertiary carbon free radical. And again, here and here. So the unique halogenation, you have these four. I can see the final product can be very messy because it will form many chiral centers. Here is not a chiral center. If the bromine replaces the hydrogen, this will not be a chiral center because with all the alkyl group maintained the same, the molecules are symmetrical if this hydrogen replaced by bromine. And but if hydrogen replaced on this carbon, this will give us a chiral center. And same as this will give us chiral center. And so these are the reactions. So in the end, it will give you a whole bunch of product. You can see the halogenation reaction is fairly messy. Unless we have something to control the final outcome, halogenation is very difficult to use for synthesis. Yeah, they're just very hard to be selective. Unless you have some very unique structure, give you only one product. So for example, this alkane, as I mentioned, alkane is the least used for organic compound in nature for human. And mainly we use it for fuel. And how to turn those alkane, which is clearly abundant, into something useful. The first step is through the halogenation reaction. And for a smaller scale, when the chemicals used for our everyday human activity is small amount, we can use bromine because bromine is a very expensive halogen. And bromine can turn the alkane into the alkyl bromide. And alkyl bromide, next step, depends on, we can choose a different kind of base. We can either form double bond here or double bond here, depends on what kind of base we use. And then we can make alkene out of this. And once we get alkene, it can be much more useful, like we learned in the alkene addition reaction, because there are so many reactions can take place with alkene. The bromination is the most useful. If there's one site, it's more reactive than the others. The chlorination reaction selectivity is not very good, as you can see from the earlier table. So the chlorination reaction only used when the alkane is highly symmetrical. When you have highly symmetrical alkane, then you have only one or two types of hydrogen. So you might have a different carbon have a such hydrogen, but if only one of those hydrogen react, you get only one product. So for example, this is how if I react to this, give you chloride. If I go to this one and give you this chloride, will be same as the first chloride, no difference. So highly symmetrical, we can use a chlorination reaction because the chlorine is cheap, but not very selective. So that's the, yeah. There's halogenation. There's issue with halogenation. In the future, we just limited use. The alkane halogenation, we can make halides, and halides, as I mentioned, is very useful because the use elimination reactions. Use elimination reaction give you alkenes, or we can use a substitution reaction we learned before. Either SN1 or SN2. If I start from this, use a substitution, adding some different functional groups, and that'll be the SN1 substitution because stability of a carbocation. And start from the halide, it goes through the elimination. This is tertiary carbon, so the elimination will be E2. There are many bases that can do the elimination, but once you do the elimination, we can give the alkene. I should add one more. If we add a Hoffman base, okay, T-book on this halide will give us a different alkene. And in organic synthesis, start from one substrate, one reactant. Depends on the reaction condition, depends on reaction temperature sometimes. Oftentimes the solvent can give us different product. So it can be very useful. So that's how the, you can see this chapter we introduce the free radical reaction. The reaction mechanism can be very complicated, but it's a very important, useful reaction to convert the less useful alkane into the precursor for something very useful, such as alkene. And this T-book gives Hoffman elimination, so eliminate on the carbon that has less, more hydrogens. This we learned before. And by the way, in our test, in our midterm exam, there'll be quite a few questions dealing with those selectivities. So, okay, only there's one special alkene they're very special because when there's carbon-carbon double bond, the alkene structure in the alkene, the allylic position becomes very reactive. And you can see the chemists studied bond energy, and we found out here's double bond. The hydrogen attached directly to the double bond. Bond energy is fairly high. This is fairly high energy, which means not being reactive in the free radical reactions. And then you look at the this carbon. This carbon, if dissociated from radicals, which is here, the radicals will not have resonance. It is simply a secondary carbon radical. And so you can see the energy is still fairly high, but lower than the bond with the alkene. What is interesting is the carbon-hydrogen bond link with double bond. This we call allylic. Allylic hydrogen, the bond energy is 80 kilojoule less than the direct on the double bond, or complementary with secondary. This is unusually low bond energy, which means your reaction activation energy be less and reaction faster. It can give you the major product. So with this bond energy, due to the low bond energy here, which means the free radical attack become very easy to attack this position, give you a very stable carbocation, the carbon radical, and give us final product. So the low bond energy, it should give us the most reactive position due to the lower, more stable carbon free radicals and the lower activation energy and faster reaction. Faster reaction gives major product. So the reason because the resonance, and you can see the this bond energy is very low. Once you lose the hydrogen through the reaction with radicals, and the reaction with radicals, there are quite a few. It can be the chlorine atom take away, or the radical take away the hydrogen, or some other atoms, some other ions. Can be there, whatever radicals here can take away. Either way, give us radicals, and this radical is stabilized by the double bond through the resonance. So the resonance is sort of similar as the normal resonance we did before. But a radical resonance difference is the single hook. Single hook. And you need 2 hooks to form 1 bond instead of a 1 arrow, 1 double barbed arrow to form 1 bond. And anyway, the resonance that'll basically be able to shift the radical into a different location. And so because the resonance makes the radical very stable, and with this kind of alkene, the bromination reaction gives us the allylic position replaced by the bromine. Okay, so the reaction gives us exclusively the allylic position bromination product. By the way, this is never seen before. Reaction did not take place on the double bond or somewhere else. Well, even though this reaction is very quick, the simple addition reaction, which means these 2 carbons each combine with the bromine in the N-type position, that reaction, it still competes. It competes with this reaction. But this reaction is so much faster. The competition is very weak. So the allylic bromide should be the major product. And to avoid the halogenation reaction, which means we try to get rid of the Br2. Because once you use Br2, there's a possibility you get the bromination reaction. The bromination reaction. So we use the NBS to produce the Br bromine radicals. And NBS, this is the full name of the NBS, is N-bromo-succinimide. So basically the nitrogen form bond with a bromine is a fairly stable molecule. Succinimide is basically a amide. So we have the amide as a product. This is the amide, sorry, this is amide. The hydrogen replaced by the bromine that'll give you the bromo-succinimide. And this is actually, we short name NBS, oftentimes used in the bromination reaction to replace the Br2, because Br2 might have a side effect, this side product, byproduct, which is addition reaction. To avoid that, we use NBS. So this NBS, this nitrogen bromine bond is very low bond energy because the radical is very stable, free radical very stable, stabilized by those double bond. It's through the resonance. And let's see. So basically, that's what happened. The resonance will give us, if you draw one of the resonance structures, that becomes this. Yeah, so there are 2 carbonyls. Double bond stabilize the free radicals as a fact because of resonance. And we use this compound to do the halogenation instead of bromine, the Br2. And the reaction happens very similar as before. We got initiation. This is initiation, sorry, this is initiation. Initiation brings the bond from the bromine atom, which is radical. Propagation, just like we've seen before. It gives you the stable radicals, stabilized by resonance. And the next step in the propagation is this carbon radical react with the reactant, bromine, the Br2. And that'll give us, this is the product. It's a major product. Where at the same time, the bromine radical, the bromine atom, being recovered. This has been regenerated. It was used in the first step in the propagation, but regenerated in the following step. So the bromine atom being recovered, and we have a reaction. Termination does the same with C before. The termination not particularly interesting. It's just and also the this product, okay, succinimide. The very first step gives a radical. Bromo succinimide break the bond, release the bromine atom. The remaining is a radical. This radical, it can also help the propagation by reacting with the product. Okay, this is the product in the other reaction. But between these two, it is through the hydrogen abstraction. It regenerates bromine atoms. Regenerate gives all right, so this is the nitrogen gained hydrogen, and the bromine now becomes a radical. So NBS have two ways to produce the bromine atom free radicals. One is directly dissociate, give you the bromine atom. The other one is the radical react with the bromination product. Okay, by the way, this is a bromination product in the bromine reaction with this compound. In this way, they can also generate the bromine atom. So that's very nice. It works out very well. Anyway, with the resonance, is sometimes, and actually oftentimes, with resonance, when you have an allylic position, have a carbon hydrogen, and this carbon hydrogen will supposed to give you low bond energy, easy form product. So with this structure, this reactant, this is the allylic position from the double bond. And so the carbon radical formed here would have been stable. And the next step, it react with the bromine, give you a final product. So this should be the major product. But what do we find in the experiment? It is we actually get two products. Okay, we get two products. And this product, based on the position of the carbons, I kind of highlighted where's the position of the carbon. This what it was. This is what it was. So basically, if you look at this product, you notice the double bond seems like shifted. So where does this second product come from? If you remember the carbocations, we have a lot of carbocation reactions, SN1, E1 reaction. The rearrangement taking place. The rearrangement can either go through the hydride shift or alkyl, the alkyl shift. But how about this? Is this rearrangement? The answer is not because of rearrangement, it's because of resonance. Okay, it's because of resonance. So here's why. The very first step, this NBS produces bromine, the bromine atom. And the very first step of reaction, it is, I just skipped the step how to form the bromine atom, like we've seen before. The key step reaction is a bromine atom. It reacts with hydrogen. It's basically called a hydrogen abstraction. Single electron form bond. And this bond have two electrons. One of the two electrons go here to form bond. It's kind of cooperation. Cooperation between the two unpaired electrons to form bond. And there's one more electron on this bond. This electron go here. So the first step, what you get, it is a carbon radical. Well, the carbon radical, it has a single electron in the p orbital. This p orbital is parallel, interact with the p operator in the pi bond. So the resonance, it is the pi electrons shift location. And this pair of pi electrons, electron split. One go form the double bond, the other one go just becomes the unpaired electrons. So here, because of resonance, what we get is a new radical. The resonance gives us a new location for the unpaired electrons. So this is basically explained. The very last step, this radical will react with the bromine atom or react with HBr, whichever way will give us final product. And the reaction to get to the final, it typically is a reaction with HBr. Both this intermediate will give me this product. The resonance structure reaction, take the bromide, give us the other product. And so that's why the with a lytic carbon hydrogen available, you might get more than one product. Okay, question for you guys. Which one should be more stable between these two carbon radicals? Which radical is more stable?
The first one.
Because?
The tertiary carbon and...
Yes. And double bond. So because of hyperconjugation, because there are so many CH bond here. Yeah, tertiary carbon with double bond. And this is the primary carbon radical. Yeah, this should be less stable. This one should be the major product. And this should be the minor. So that is how the reaction takes place. If I use a different example, okay, let's find use a different piece of whiteboard to draw. If we have different alkene, okay, let's say we have alkene looks like this. We have an alkene like this with NBS. How many different kind of product we can get with NBS? So basically, by checking how many allylic positions, here there's two hydrogen here, two hydrogen in this position on this carbon. Here 3 hydrogens. This is also, by the way, is allylic. There are 3 hydrogens on this carbon. So the product we can get, it'll be quite messy. We can have the bromide here. And bromide on this position. By the way, these two are isomers, are different. Okay, what else product we can get? Are there any other product we can get from this reaction? We need to think about it. Let me see. We would have 2 kind of radicals. We will have this is one of the radical, which will give me this product. And the other radical, that's where this compound comes from. It should be here. Okay, so we have 2 radicals. And then let's think about the resonance, okay? Because the resonance of this radical will give me this product, this radical. So between these two, through resonance, I can get two completely different structures. And how about this? This one, I can also do the resonance, but let's see what we get. This new radical is exactly the same as this, no difference. So the resonance of this radical with double bond will actually give you no new radicals. So, which means, sorry, this radical here. The reaction we add in the bromine on this radical will give me same as this product. So between these two, no difference. They both give me the same product as here. Okay. All right. So how about this pair between these two and this radical gain bromine becomes a halogen. That should give me a different product. Okay, so the bromide you can get, so far I'm seeing three. I've seen this, and this, and this. Okay, let's kind of compare these two. I'm not quite sure I'm getting new product. Maybe I'm getting just the same product, just a different location. Is this a new product different from these two boxes? I am not so sure. We need to look closely. The inorganic in any class, when you get some answers, always have some kind of self-doubt. It's a healthy self-doubt to think about it. So let me see if these products are different or they might be the same. Okay, the only way we can compare all these three different structures by visual, but that's not a good way. I realize, maybe you have realized too, it is by naming. Okay, let's name these three products. If you get the same name, then they are the same product. You get a different name, then a different. So by naming, okay, we don't need to complete the full naming. So this is the, let's kind of use different colors. Okay, with this alkene, which carbon is number one, by the way? By naming the alkene.
It's the one on the right, like that yeah, where that pencil is, yeah.
Yep.
That's
so number three was a bromine, number one was the alkene, all right? And how about this one? This is number one, of course. Number two, well, number two can go either this way or that way, and normally go this way. So this would be 3 and 4. So this is kind of funky, is the methyl group, but a bromomethyl group. Position 2 has a bromomethyl group. Okay, you can see the difference. And this compound, oh, this compound is interesting. Which one should be number one?
the one on the left with the substituent with the methyl.
This one, number one?
Yeah, I think so, right?
Okay.
Because it's the longest chain.
I would disagree because this will give you all the substitute and give you a higher number if it's just number one. If this number one methyl group here, you got 3 methyl, and this would be 3 bromomethyl. Let's try it here. If this number one, if this number one, this would be position 2 has a bromomethyl. Is it better? If this number one, position 1 has a bromo group, position 2 has a methyl. So
okay.
Yeah, I would lean toward either this or this. These two kind of hard to compare. I kind of leaning toward this is better. This is number one. If this is number one, this is the naming will be 1 bromo, 2 methyl. And the final product, we need to worry about ZE configuration, because the methyl group here versus here is completely different product. So this have a ZE designation. But anyway, the whole point is this: we're not complete naming. We're just comparing. Are we getting new product? Just by checking naming, you can see these three completely different. You got a 3 different product. So this is actually a very good example to practice on, to think about the how many mono-bromination product can get. We need to consider the stability of the radicals and also the resonance. This is the resonance. The key, it is the resonance. The resonance gives us more possibilities. Resonance gives us more possibilities. But sometimes we have to kind of do the self-check. Maybe they're not getting completely different product. So that's how this is the reason why I enjoy organic chemistry so much. Because if you learn the knowledge, you can see you can have more critical thinking, and not only just numbers. Now I have a 3-dimensional critical thinking, and always have a healthy, a little bit healthy dose of self-doubt. That's already helpful. So that's about little side distraction on the NBS react with the allylic carbons. Okay, so we're getting back to the lecture. Yes, there is lecture. The last part, we just kind of explain what happened with the Anti-Markovnikov addition. This happens in the alkene reactions. Alkene with hydrogen bromide in the presence of peroxide. And why we get an anti-Markovnikov product? Why the hydrogen add on the carbon with less hydrogen? Okay, so if you remember, Markovnikov is when the no catalyst, no peroxide, and the hydrogen add to the carbon with more hydrogen. Okay, that's Markovnikov's rule. The anti-Markovnikov when you have peroxide. Peroxide, the reaction completely different. And by the way, learning these two reaction pathways is very helpful for the future discussion about the synthesis. And as if you get into after this midterm, the last months will be focused more kind of use the synthesis as a guiding tool instead of just memorizing those tens of reactions. And there will be more reactions in the future chapter, but those chapters are basically have a synthesis in our mind. Anyway, the difference between these two is the Markovnikov goes through the carbocation intermediate, the tertiary carbocation more stable, therefore you get most that reaction product. The anti-Markovnikov is a free radical reaction. So we just quickly go over how does the reaction takes place. The peroxide, if you remember, the oxygen bond is very high energy bond or low bond dissociation energy. High energy bond, very unstable. So it'll break homolytically from the 2 oxygen radicals. We call it oxy radical, alkoxy radical. The alkoxy name comes from the alkoxide. Alkoxide is the anion. The alkoxy radical is just a free radical. You can see the bond energy. This is very low energy, so easy to break. Give you the free radicals. The radicals will react with one of the reactant, which is HBr, and give you forming the bromide. These the initiation step actually have 2 reactions. That's the goal. Final goal is to form the bromine, the bromine atom, which is radical. This reaction, the entropy change is almost negligible, but highly favorable because the exothermic reaction is highly favorable. So that means the reaction product, the bromine is very stable. And then this reaction, the bromine will start all the following reactions. The bromine will react with double bond. Okay, this is the This reaction is direct react with double bond. So it's kind of interesting to think about. There are a bunch of allylic hydrogens. Why they don't react with hydrogen and getting the addition reactions? Well, that's what the chemists discovered in the study those reactions. We did not find much the allylic substitution reactions. Instead, the reaction with double bond becomes a major reaction, and the reaction produces another carbon radical. And this reaction exothermic, so that means favorable in the thermodynamics. This radical very stable. And the propagation reaction, eventually we need to regenerate the bromine atom. So to do that, need to react with the reagents, HBr, the reactant. And through the hydrogen abstraction, give you the recover the bromide. Meanwhile, getting this as my product. This is our product. And the bromine go back to the same cycle, so being self-sustained. And okay, the reaction can actually take place on the other carbon as well. I need to use different color. If the reaction happens on this carbon, we will get a different radical. Okay, so we'll get a different radical. If reaction happens this way, will give me a different radical. But the reason why we don't see this give me final product, it is because secondary radical not stable as the tertiary radical. That's why this is very, very minor product, because stability higher, low stability, high energy state. So that's basically explained how that's happened. We have a Anti-Markovnikov as final product. Termination, just many others. The free radical, just radical react to each other. The radical react to each other is stop the whole thing, stop any possibility of further reaction. Okay, so next, the last part, we get into some thermodynamics, but I think we're getting to the wrapping up the whole chapter. The free energy change for the reaction. Okay, by the way, free energy change is related to the equilibrium constant. And the equilibrium constant for this reaction, if we reach equilibrium, which one is more favored? How the temperature affect the reaction? The free energy change, as we learned in the general chemistry, it comes from enthalpy change and entropy change. In the halogenation reaction, it is basically looks like a substitution reaction. The amount of molecules between reactant and the product is the same, no change. There are no change in the number of molecules in the reaction. So therefore, the entropy change is negligible. And since the negligible entropy change, that also means temperature have very small impact, if there's any reaction on the impact on the equilibrium. Just because if delta is already small, then the temperature change, the total combined effect was still very small. But all these reactions, if you study the enthalpy change, we can use the bound energy to calculate. I did not test on the bound energy effect on the reaction. We have learned in the general chemistry. And so basically with the same methane react with different halogens. And if you study the enthalpy change for each reaction, we notice quite dramatic difference among those reactions. The fluorine reaction is highly exothermic, highly exothermic. Chlorine is intermediate, it becomes much less. Bromine is even less. So you can see the trend is it becomes less and less exothermic. Reaction with iodine, reaction with iodine is actually endothermic. So you can see among these 4 reactions, among those halogens, reaction, the delta G, it becomes less and less negative, which means equilibrium constant becomes smaller and smaller from fluorine to iodine. The iodine basically is not favored. When you have the iodine try to react with methane, the reaction should not be moving forward because the forward reaction is not spontaneous. You get a positive delta G. Only up to the bromine, you have a small but not too small. So that's the equilibrium favor the halide up to bromine, and iodine will not go through will not be favorable for the reaction. And the fluorination and the iodination, both reactions in practice we don't use them. The reasons are very straightforward. The first reaction, it sounds like a very highly favorable for the forming product, but the reaction cannot stop because those hydrogen on the fluoromethane, there are more hydrogens. So in the end, it will keep reacting until it gives us carbon tetrafluoride. It can stop. It cannot be selective. So it's not useful. And also the fluorine is highly dangerous. The reaction produces so much heat, it's almost explosive for this reaction. Iodination reaction, as you can see, the delta G is positive, so cannot form product. So only the chlorination and bromination. And between these two, bromination. Okay, so if you look at delta H, what does this tell you? Chlorination is a little more exothermic and more than the bromination. Chlorination more favorable for the product because the more negative delta G. And the chlorination reaction, if you look into the energy diagram, it has low activation energy for the first step. So that means chlorination reaction is kinetically favored. Okay, it has low activation energy, so it should still go very fast. And also the energy change for the reaction is highly exothermic. And so this reaction is both kinetically and thermodynamically favored. The delta H, negative delta H, it means thermodynamic favored. The small EA, very small, means faster reaction, so kinetic favored.